All right, we're going to take a look at tables of probabilities, tables and probabilities, excuse me. It's very important that you read the instructions and make sure that you are drawing from the correct table. Once we get that, we will just set up our probability statements. So we've got a table here that's talking about adults, and then we've got our age categories 18 to 34, 35 to 44, and so on. And we want to point out real quick, the total number of people polled was 530. And then we can see each little subgroup has its own total as well. But when it was all said and done, we had 530 that were polled. So that's an important part to know. So first thing we'll do is we'll look through this thing and see what it exactly is we're looking for. It says, if an American adult is randomly selected. That first line is going to tell us where we are drawing from. Since it doesn't pick one of the subgroups, the number that we're drawing from is 530. So it says if an American adult is randomly selected, what is the probability that he or she uses social media? Well, it doesn't tell us which age group that it is talking about. So if it's not telling us which age group we're talking about, then we just need to first find we're talking about the social media group. It did not define which age group, so it's talking about the entire population of adults. So when we set up this probability statement, it would be 338 divided by 530. So when we do this, if we put this into our calculator, it's going to give us a decimal which would round to 0.64. So you got about a 64% chance. About a 64% chance of choosing an adult that uses social media. All right, let's move on to the next one. So we see we are looking at an adult that is randomly selected. So again, we are drawing from the entire population, which is 530. What is the probability he or she is 45 to 54 years old? Now, this does not clarify whether we're talking about social media or non-social media. So if we're not distinguishing between one or the other, then that means we are drawing from the entire 45 to 54 population, which is 140. So our number is 140 out of the 530 completely polled. Again, I'm going to be rounding on this, so this, once I put it in my calculator, comes out to approximately that. And anytime you round, you have to denote it with an approximation. Letter C, if an adult is randomly selected, again, we're drawing from the entire population. What is the probability that he or she is 35 years old and a social media user? All right, that means it doesn't say or, it says and. So we are going to draw from the 35 to 45-year-old list and the social media user. So our line would be the 89. So my probability is the 89 people out of the 530. Again, I'm going to be rounding on this, so it's going to be about 1.68. And again, make sure we understand that this is about 16.8%. Letter D, again, we are drawing from the population because it starts off by saying, if an American adult is randomly selected, what is the probability he or she is 35 to 40 years old? Now we use the word or. Now, or changes everything. Or changes everything. So we're using or a user of social media. So this is not mutually exclusive events because you can be 35 and a social media user. So this is going to be one of those statements where we add our probabilities and subtract any overlap that we might have. So let's take one at a time. What is the probability he or she is 35 to 40 4 years old. Well, 35 to 44 years old is 125. So we will take our 125 out of the 530. And then we're going to look at our or a social media user. Well, our social media users are 338. So we're going to add those to our list. 338 out of 530. But again, we see that we have counted the 89 35 to 44-year-olds that are both social media users and in the age group. So what we'll have to do is subtract our 89 away. So we will subtract 89 out of 530. Now, since we have all common denominators here, we can combine everything on the top. That would be 333. When we combine all our terms, my numerator is going to be 374 out of the 530 people. That fraction does reduce, but what we need to know is that it comes out to about a 0.706 probability, so just under 71%. Next thing we'll look at is when we see the word and. We're talking about the multiplication property on this. So when we see the word and, this is when this is going to happen. You might want to put that in your notes over there on the side. We are having this when we are talking about and situation. So the probability of A and B, that the event A occurs first in the trial and B occurs second. And the order does matter in these things. To find the probability of A and B, we must multiply. Must use multiplication. All right, so let's learn how to read these things first of all. Probability of A and B. So the way that we are writing this, the probability of A is pretty simple. Probability of A. On an and statement, we have to multiply our probabilities. So what we will do is we will multiply the probability of A by this little statement that you see right here. This statement here says the probability of B, and whenever you see that nice solid line right there, nice solid line that's going down between the B and the A, that's saying given that A has already occurred. So that's a much abbreviated way of saying that. That's saying the probability of B, that line means given that A has already occurred. But we don't have to write all of that out. We just need to understand that that's what it's saying. All right? Two things we need to pay attention to is the type of interactions we have. Are the two events independent of one another? What that means is one has no effect on the other. One has no effect on the other. And if the first selection does have an effect on the second selection, this is what's known as dependent. Independent and dependent. We need to recognize these as we go along because it will change both our numerator and our denominator. A lot of times it's something as simple as replacing a card. So if we're talking about the drawing a card from the deck, it's a matter of what do we do with that card once we draw it. Is it replaced in the deck, meaning we put it back, or do we keep that card out? Because if we replace the card in the deck, we still have 52 cards in the deck for our second selection, but if we set the card out to the side, then we only have 51 cards in the deck. All right, and notice this, when the two events are independent, the probability of A, B, given that A has occurred, will just be the probability of B. And that makes sense, because if A is not going to affect my probability of B, because they're independent events, then it's not going to change my probability. Drawing the first will not affect the second. And we have a couple of examples of that we will talk about. All right, let's first decide if these are independent or dependent ideas. It says you draw two cards from a standard deck without replacing them. Without replacing them means I'm taking the card out. If I draw the king, I'm going to set it to the side. So if I do that, now it is impossible to draw that king, and we're drawing from 51 instead of 52 cards. So this is a situation where we are talking about dependent situations, because my probability of the second will depend on what happens on the first. It is affected by it. All right? What is the probability? We're looking at A. What is the probability that you draw 2 kings in a row? And again, we are not putting the cards back. Well, there are 4 kings in the deck. There's 4 kings in a deck of 42 cards. 52 cards, excuse me. So if I select that king on the first one, now on statistics, when we're doing these, as improbable as it may seem, we treat it as if it happened. Is it likely that I'm going to draw a king? No, it's not really that likely. But we're just going to continue on as if it's a certainty that it happened. So our next scenario, since I've drawn that king on the first one, it's no longer in the deck. So there are only 3 kings. And not only are there only 3 kings, there are only 52 cards or 51 cards in our deck because that king is sitting out to the side. So when I calculate this, I put it in my calculator, obviously, this is going to be a 1 out of 221 chance of this happening. So my chances of drawing 2 kings at random is 0.0045. So if we're talking about a percentage, we're talking less than 1% that will happen. All right. Now you notice I'm not going to worry about common denominators because we're multiplying. When we're multiplying, common denominators are of no help to us. So let's move on to B. What is the probability of selecting 2 diamonds? Well, the diamonds are 1 out of 4 cards in the deck. It's technically 13 out of 52. You can put it that way, that's fine. It's the same thing. Your calculator will recognize it as the same. So drawing a second diamond, well, now there were 13. So now there's only 12. And there were 52 cards, now there's only 51. When I multiply these out, this is going to give me 1 over 17. Again, I let my calculator reduce my numbers for me here. I don't really quite understand what 1 divided by 17 is as a decimal, but, or excuse me, as a fraction, but as a decimal, we will recognize that it is 0.059. So we're talking about just under a 6% chance of this happening. You got a 25% chance of the first scenario happening, but again, our scenario continues to decrease. So a lot of different ways to not draw 2 diamonds in a row. And then lastly, a king and then an ace. Well, if you think about a king and then an ace, since we're replacing these, we're looking for one specific card here. It's a lot like A. We have 4 kings out of 52 cards. When I select that king, I'm next going to try to select an ace. Well, there are still 4 aces, but there are only 51 cards. That is still a dependent event. Even though it didn't change my odds of selecting an ace very much, it did change the odds. This ends up being 4 over 663 when they get reduced, which is approximately 0.006. And you can see it's very close to the kings because it's a very close scenario here. Now, keyword on number 2. With replacement, meaning once I select that king, I get to put it back in. So my scenario for the first king was 4 out of 52. There are 4 kings, 52 cards. Well, since I put that king back, I can still select that king, so there are still 4 kings in the deck, and there still is 52 cards in the deck. You are welcome to put that as 4 over 52 squared, but when we calculate this, my calculator tells me 1 over 169, So my chances of doing this are 0.00592. Now when we compare that to not replacing, you see it's still unlikely, but we can see the chances have improved. So we're going back to 2 diamonds. Let's just rush through this one here, 4 out of 52. The second diamond will still have, excuse me, wrong on that. Diamond is 1 out of 4, 1 out of 4, or 13 out of 52. But we're going 1 out of 4. Since we put the card back, we are back to 1 out of 4. This is 1 out of 16 chance. And 1 out of 16 is approximately 0.0625. And then our king and ace would be 4 out of 52 times 4 out of 52. The same probability of selecting 2 kings. Since we're putting the card back, the parameters have stayed the same. All right, consider a quiz with 2 questions, true or false, and a second question with multiple choice. And the multiple choice A through D, so there are 4 options. All we do on these is we need to multiply our probability. So the probability on the true false is 1 out of 2. The probability of the multiple choice is 1 out of 4. So my probability of guessing at random and getting both right is a 1 in 8 chance. All right, I'm going to leave you guys with the next dot under C there. And then you've also got your table, so you guys can work with these and solve those out. And by the way, the probability is already given on these. We still do the same thing. We multiply. We'll just look at this one actually. Probability of E, probability of F and E. Well, we're going to have to multiply these together. So my probability of E is 0.4, excuse me. My probability, again, of E is 0.04. And the probability of both is 0.21. So remember, when we're doing this probability, we have to multiply the probability of the first, which in this case was given to us. Probability of E, times the probability of F, which we don't know. That's what they're asking for here. And it's actually of E, F given E, should equal our probability of E and F. So in this case, we have the P of E, it's right here. We don't have the probability of F given that E has happened. So that will be our X value because it's an unknown number. And just like any other algebra, anytime we're trying to solve for X and we have multiplication, we are going to divide to get rid of this. So we divide by 0.4. And X equals 0.525. So our probability of getting F, given that E has happened, would be just under 53%.